Hello, my name's Jesse Clarke and I work for ProClimate as the Building Science Manager for Australia and New Zealand. And today I'm going to be talking about weather resistive barriers and the design and implementation to get effective weatherproofing systems. The first thing we need to ask, or the first thing we need to understand when designing weatherproofing systems is what is weather? And weather is the state of the atmosphere at a particular place and time as regards heat, cloudiness, dryness, sunshine, wind and rain. And the important thing there for weatherproofing systems is a combination of wind and rain. So what we're fundamentally trying to do when we design weatherproofing systems and utilization of weather resistive barriers is to manage the external rain loads on facade systems or on the whole building envelope. And in particular for facade systems, how much it rains in any given location will determine how we need to design those or how effective those weather resistant barrier systems need to be. And as you can see from this chart, that in some places in Australia it rains a lot, although it's commonly referred to or thought of as a dry country. Along the coastline where majority of people live, particularly on the east coast of Australia, there's quite a significant amount of rainfall. The other thing we need to consider when designing weather resistive barrier systems and weatherproofing systems is the climate conditions in which you're designing your building. So in cooler climates where buildings are normally heated, so in cool temperate regions and you've got warm humid air on the inside of the building, this can actually push water vapor into the structure. In the tropics, when you've got lots of water vapor in the air outside the building, then the air conditioning can suck water vapor back into the building structure. So we need to understand the properties of the materials used to weatherproof our buildings to make sure that we don't trap moisture or create high humidity within our construction systems. So when you overlay those two things and you have the combination of external moisture, how much it rains, and the internal conditions in the building, whether it's heated or cooled and whether it's dehumidified, and the water vapor pressure or the amount of humidity in the building will all affect how we should need to design the building envelope systems, including the insulation, to make sure that we can have dry, healthy, durable, and energy efficient buildings. So the second question we need to ask is, what is a water barrier? And we need to understand that there are no perfect barriers, it's just a threshold. So everything has different degrees of how waterproof or how good they are at stopping water from passing through that particular material. The water barrier threshold set for pliable building membranes in Australia and New Zealand is defined by 4200 Part 1, and in Australia, the threshold is set at 100 millimeters head of water. So that means the membrane has to be able to stop the water leaking through it under a 100 millimeter water column. So that's a little column of water 100 millimeters tall, which represents about 1 kilopascals. And it has to hold this water for 24 hours. That's the minimum threshold for a water barrier in Australia. In New Zealand, it's even less. It's a 20 millimeter head of water representing 200 pascals for a weather resistive barrier used on a facade system. But there are products on the market, pliable building membranes, that can hold as much as 10 meters column of water. So that's a significant amount of pressure and still not leak water through the actual material itself. And this is an image of the ProClimate Solitex Mento product at 260 centimeters head of water. This is 26 kilopascals of pressure, and you can see the bulge in the membrane there from the pressure and still no water leaking through that membrane. So what can happen if weather resistive barrier membranes are just engineered to meet the 100 mil head of water is that if they come under any significant pressure when water is present, it could force water through the membrane itself. The other issue is that this type of membrane commonly, if it comes in contact with any materials or any chemicals that can act as a surfactant like oil, grease or tannins from timber, then it can actually lead to the water being able to pass through the pores of the membrane and not acting as a water barrier anymore. So Now we know that the membranes need to be a water barrier, so they need to meet the water barrier threshold of 100 millimetre head of water as defined by AS/NZS 4200 Part 1. In New Zealand it's only set at 20 mils, but 100 mils is much better, and even taller water columns to get above 1 kilopascal of pressure is preferable. So the next question we need to ask is, what is a wind barrier? And the answer to this question is, it's the system is what counts, and the junctions and seals make it work. So when we go to full-scale weather testing under AS 4284, then it becomes apparent that the weather-resistive barrier system must resist the wind pressure. It must have sufficient tensile strength, must have sufficient edge tear strength, must have sufficient burst strength to maintain its integrity under the wind load in which it's designed to operate. And the weather resistive barrier generally sits behind the cladding system, and it manages that wind pressure behind the cladding system. So the cladding systems in a well-designed system aren't airtight, and they're not 100% watertight. They've actually got gaps and cracks in them, which means that the weather-resistive barrier behind that cladding is actually the air barrier and the water barrier that sits behind that cladding system, and makes the whole system function properly as a weatherproof system. So when we go through that full-scale facade test under AS 4284, the first thing you do is put the design wind pressure straight onto the facade and try and force the weather-resistant barrier into deflection, essentially stress the seals on the weather-resistant barrier system. So in this case, if it was a 2 kilopascal design pressure or serviceability limit you're designing for, you would put 2 kilopascals of pressure onto that facade. I'll get into more detail around what kilopascals actually mean a bit later, but you put that pressure on, the membrane will deflect and it will stress those seals. Then you suck the membrane off the wall and it deflects the other way, stressing the seals and everything the other way. So what we're trying to do is just essentially break the seals on the system. Then what you see is when you suck that membrane off, you actually get deflection of the membrane, and that can be quite significant, and it's dependent on the pressure on the system. The more pressure, the more deflection you get. And this will always happen with pliable building membranes or flexible building underlays. So you get this scenario where you're actually sucking the membrane off the wall and deflecting the membrane and stressing the joints, and pushing it onto the wall and stressing the joints in the opposite direction. And the pressure limits to which we're designing, in that I indicated it was 2 kilopascals, but it depends where you are. You may not be designing for a 2 kilopascal limit. The serviceability limit is what is expected to be present on the facade in the operation life of the building. And if we chose a limit of, say, 1.5 kilopascals, then that serviceability limit covers most scenarios in residential housing across Australia and New Zealand. It's only in really the corner zones of buildings that you get high pressure in wind categories N5 and N6, which is the highest cyclonic regions in Australia, that you may need more resistance to pressure in residential housing. So 1.5 kilopascals generally covers most residential construction in Australia and New Zealand. It's just when you start going up to high-rise buildings or up to really high-level cyclonic regions that you may need to consider higher pressure systems. So what happens when we have wind and water at the same time? What happens when they coincide? And basically, brands highlighted this back in 2010. A lot of research have done on weatherproofing of buildings, and they said if not provided with effective air seals, any gaps, joints and junctions in the wall cladding can become air leakage bars that can carry water when present. So it's that coincidence of the wind pressure, small air leakage bars that entrain water through the cladding and or through the weather resistive barrier and into the actual insulated structure, and that's not what we want to happen. So if we look at a weather resistive barrier system and we put all the rain load directly onto the weather resistive barrier system and then add pressure to that system and we try and force all that water through any gaps or cracks in the weather-resistant barrier system using the wind pressure, then this is a very onerous test. And what I'm showing here is a 1.5 kilopascal pressure with spray nozzles onto the weather-resistant barrier system. If we were to test just the weather-resistant barrier under this system, essentially what we would be testing is something that looks like this, where you actually lay the system flat, and then if we put 1.5 kilopascals of pressure onto that, essentially what we're looking at is 150 millimeters head of water, 150 millimeters depth of water, forcing water down, trying to force the water through any gaps and cracks and imperfections in that WRB system. And to be honest, that will leak. It will leak. It's not going to be 100% waterproof under that scenario. It would have to be built like a swimming pool. So what does that actually mean, that 150 millimeter head of water? It means you've got about 150 kilograms per meter squared of pressure pushing down. So you're going to deflect that membrane. That is equivalent to about 1,500 newtons per meter squared, which is 1.5 kilopascals of pressure down onto that membrane. And that is equivalent to about 1 Thomas van Ramstonk per meter squared. So it's quite a significant force pushing that membrane down, trying to force water through any gaps and cracks and imperfections. If we wanted to make that more waterproof, the membrane doesn't need to be 100% waterproof. What we need to do is separate the water from the membrane. So if we can magically levitate that water up off the membrane, then there's no way that membrane can leak. If we're not in the horizontal position, but we're in the vertical facade position, the best way to separate that water from the weather resistive barrier is to put a cladding on. That means the cladding deflects most of the rain. Let's say 99% of the rain is deflected by that cladding, and the weather resistive barrier only has to deal with a very small portion of that rain load. And this is how we design and develop and implement facade systems that are highly weatherproof. So after we've set in that structure, so putting pressure onto the membrane and sucking it off the membrane to make sure that it's been stressed and all the steels have been stressed, you put water onto that system with no pressure at all. When you put water onto that system with no pressure, it's easy. It doesn't leak because the water just dribbles off the cladding. The next phase is when you start introducing pressure into the mix, and when you do that, you start with 30% of the design pressure. So 30% of the 2 kilopascals, about 600 pascals, we put onto that facade with the water spray nozzles and see if we can force that water through the cladding, then through the WRB system to the inside of the structure. If that passes, basically you turn the pressure off, you turn the water off, and if it passes, you won't see any water on the back of that membrane system. But the test is not over. If there's no water under the first stage, then you go to the next stage, which is cyclic pressure testing, which means that you're actually stressing that membrane in positive and negative pressure with water spray onto that system. And you're trying to stress all the joints and loosen the weather-resistant barrier system and force water into the structure. So this is an onerous test, and what you're doing here is simulating gusting wind under rain conditions with water hitting the facade. So what a weather-resistive barrier actually needs to be to get effective weatherproofing is it needs to be a water barrier and it needs to be an air barrier by definition of AS NZS 4200 Part 1. So weather-resistive barrier is not actually defined in that standard, but this is what you need to make a weatherproof building. You need to have those two properties, and those air barriers, or the air barrier membrane, needs to be connected and sealed at all junctions and overlaps. And this is how you achieve effective weatherproofing for the building code. So this full-scale weather testing which is undertaken is essentially what you're testing for, and you're testing the effectiveness of that water barrier and the air barrier system to hold out water and under wind pressure and make that system weatherproof. So the next question we need to address is, what about other components? And the answer to that is the system is only good as the weakest link. And so what we're talking about is how the WRB connects into other components within the system, like windows. So when we do a full-scale facade test, we're not just testing a flat facade. That's too easy. What we need to test is all the details. So we need to address this structure here, which includes the details of how to connect into windows. It includes parapet details, box gutter details, penetrations like pipes and how the WRB needs to connect into that, details at the base of the wall, at the top of the wall, and possibly in some circumstances the WRB needs to wrap around soffits. But the test is essentially testing the combination of the WRB in combination with the cladding material. The cladding's there, as I discussed, to deflect water away from the WRB system, and they operate together to get a weatherproof outcome. One of the very important things when looking at the integration of components into the WRB system is how you do that. And one of the ways that you're likely to fail the test is when you end up with a situation like this with a wet seal around a window. And if you have any minor pinholes within that system and you have air pressure and water present on the outside of the structure, then it can force water through those pinholes, leading to water drops on the inside and a fail of the test. Another way to address this is to use taping systems. Taping systems operate slightly differently because they are flexible. So that means if you've got wind pressure on the outside of the building, the tapes are able to flex under movement of the facade. But also as the building settles and as the building moves over time, then those seals can maintain their integrity. So what's critical to making all these systems work, the integration of the WRB into all of the components, is the details. And this is fundamentally important. It's about installation, and it's about installation. And that's why people like Airboss Dan are so important, because he's out there training people on how to actually integrate all these components together and make the system actually work. So if you're not following him already on Instagram, please do. So how airtight is the external WRB system? So now that we know that the more watertight it is, the more airtight it is, and the more airtight it is, the more watertight it is, it goes hand in hand, this external WRB being airtight and watertight at the same time. So then it leads to other questions. So we're testing this system in the test rig. We've built it all up and we've got the components within the system all connected up. And it's all designed and it's all installed to be, well, using water barrier materials, but also using air barrier materials to take the wind pressure, but all the connections are really well done. So we'd say that's going to be an airtight system, right? Yes, it is. It does deliver a degree of air tightness. And under the test regime under AS NZS 4284, it requires you to test the air leakage at a given pressure. And at 150 pascals, negative and positive pressure, you get 0.59 or 0.56 litres per meter squared per second, which means that it's quite airtight. But how does that actually relate to ACH 50? We've got a much higher pressure here, 150 pascals or 300 pascals, which delivers 0.88 or 0.84 litres per metre squared per second. But we can't determine the ACH 50 from these test results because we don't know what the volume of the building is, because it's just a facade test. We may be able to, or we can actually determine what is the meters cubed per meter squared per hour. So the air permeability of that building facade, we just need to do a conversion from the liters per meter squared per second. So the question then is, how airtight is this structure? And obviously after you've sealed up all the junctions using air barriers and water barriers to make sure that you've got a waterproof WRB system, then you actually do derive quite an airtight result. And when you look at this in terms of meters cubed per meter squared per hour air permeability, you get around 2 or possibly 3 at 300 pascals. So the question is, what happens at 50 pascals? Because that's when we're interested in the standardized blower door pressure. And if we correlate this back to 50 pascals, what we actually get is around roughly 1 permeability, so 1 meter cubed per meter squared per hour. If we're shooting for passive house, in terms of air permeability of the facade, we should really be down around 0.6 air permeability, because we know that based on the surface area to volume ratio of a building, permeability and ACH 50 are roughly similar, but they can differ slightly. But we would still need to target around 0.6 air permeability to even be in the ballpark to achieve passive house thresholds. So if we change that system and we say, let's put a rigid WRB or a rigid board sheathing over that system and then cover it in a peel and stick weather resistive barrier, then we end up with a fundamentally different outcome. That system is super airtight, and we tested this under a VM2 test in New Zealand, where we achieved a very, very tight facade based on a rigid fiber cement board with the Adhero Solitex Extesana Adhero peel and stick membrane over the top of it. So the next question, does an airtight WRB trap moisture? So we've made this outer layer of the structure very airtight. And this is a double-edged sword. For the external side to be an effective weather-resistive barrier, it needs a good level of airtightness that may create high humidity behind the WRB system in cold conditions. So in winter, when that WRB system gets very cold, then it may drive up the humidity behind that rigid board. So we know that our WRB system needs to be a water barrier and needs to be air barrier. It needs to be as watertight as possible. It needs to be as airtight as possible. The other thing we need to consider is the vapor control function of those layers on the outside of the structure. So is that weather resistant barrier, the membrane plus any rigid boards in there, is it vapor permeable enough to allow water vapor out of the system? And this all depends on climate. The other consideration under AS/NZS 4201 is thermal control using reflective layers. But for the context, in the context of passive house or in the context of any building, aluminium should not be used, as it runs a high risk of trapping moisture or creating high humidity behind those aluminium foil layers. So what we end up with is selecting your water barrier and air barrier such that it can be installed using proper seals and junctions to create a proper weather resistant barrier, but then selecting the right membrane or the right vapor diffusion properties on the external rigid boards and the external weather resistant barrier membranes to make sure that you don't trap moisture behind them. And depending on the type of rigid sheathing that you choose, whether it be a plywood, an oriented strand board, a gypsum plasterboard, exterior grade, or a fiber cement sheet, they all have different vapor diffusion properties and potential for trapping moisture behind them. So the only way to really make all this work is to test the system under a full-scale NZS 4284 test for weatherproofing, make sure that all the details are weatherproof, and then define the properties of the external materials based on simulation. Because we can't build a system and wait to see if it goes moldy, we have to use validated empirical tools to work out whether the system is likely to work from a drying capacity perspective and not end up with high humidity in the system. So that's where tools like WFI come in to be able to determine whether you're going to end up with a risk of mold within the system. So we need to test it, and then we need to calculate it to make sure it works. So the combination that we use of any flexible membranes that may be fully adhered to a rigid substrate, or they may not be, but either way, the combination of that flexible membrane and the rigid substrate needs to be taken into account when we're choosing the weather resistive barrier combination. So what do we need? We need to manage water and air pressure to get as close as we can to a perfect waterproof barrier on the outside. Yeah, keeping in mind real barriers do not exist in real buildings. We may get water ingress into that system, which we need to account for, and drying capacity. And we also need to manage vapor diffusion and drying through this external wind-tight, airtight layer on the outside of the structure. So we need to basically work out what's going to work in what climate we're designing for. And the fundamental philosophy here, or the fundamental question that we're trying to answer is, can you do a weather resistive barrier on the outside of the structure as the airtight layer? can we achieve passive house just with that exterior weather resistive barrier? So when we include insulation to that system, we know that in winter the outside of that structure is going to get colder. We know that the weather resistive barrier system should be a water barrier. It should have proper water control functions and features and details. It needs to control the wind pressure. It needs to be airtight as possible to be watertight. And we need to consider the diffusion control, the vapor diffusion and what's going to happen across that external boundary, and if we're going to create high humidity behind that, inducing mold growth. So the way we do this is we need to do a design calculation. The ERA DA07 is a new design application guide from ERA, the criteria for moisture control, design analysis in buildings, and what it looks at is the criteria around how you carry out a computer simulation using tools such as WFI to be able to predict whether you're going to end up with mold growth within the system. So what I'm going to show you is a few simulations that I've done on a generic sort of structure in different climates around Australia, and used in different rigid board systems with peel and stick membranes over the top. And what you see is when I simulate that out using the mold index criteria in DA07, in which the criteria for a pass-fail is set at a mold growth index of 3. If you go above that, then you're starting to get visible mold growth at that location within the structure. And on the back of the rigid WRB system for 14 different options, using rigid substrates out of the WFI database, I essentially saw a fail in every single case if I have a super airtight exterior WRB system with fibrous insulation in the structure. It basically doesn't work and you're likely to induce mold growth. If I go to Sydney, the situation gets slightly better. That's because the climate's slightly warmer. It's not so cold on the outside of the building, but we're still reaching the fail criteria or exceeding the fail criteria for that mold growth. If I take that system to Cairns and I build rigid WRB systems with membranes, peel and stick membranes over the top in the tropics, then I'm highly likely to get 0 or very little indicators of mold growth behind that WRB system. And that's because the water vapor is driving the other way from outside the building to the cool inside of the building. And that, in that case, external air tightness using a rigid WRB system with a membrane over the top works. So up in the tropics, it's highly likely we can use this exterior air tightness layer to get to achieve passive house outcomes. If we're in the cooler climates or temperates or mixed climates, we need to consider, well, how do we actually stop high humidity occurring on the outside weather resistive barrier system? We need to consider an air barrier on the inside of the structure to stop the internal water vapor and humidity coming into the fibrous insulation and then reaching the cold outside WRB. That internal air barrier can't just be an air barrier. We need to think about it as an air control layer that also has smart vapor control. The smart vapor control function is critical because we need that internal air barrier to be able to release water vapor should any water vapor come from outside the building through the external WRB system, or should any water ingress accidentally occur into that system, we need to increase the drying capacity. And what the smart vapor control is talking about is essentially if there's any high humidity within that structure, then it will start to become more permeable and allow that water vapor out of the system. And this is what we're calling an intelligent air barrier. And you may have heard other terms used such as intelligent air tightness system, smart vapor control system, humidity variable air control system. They're all the same thing, and what they're saying is that membrane is an air barrier that will respond to humidity and become more permeable under high humidity conditions. So if we use this internal air barrier in Melbourne with the same 14 scenarios that I simulated, then it basically solves that problem. You don't end up with the high humidity behind the WRB system that is going to induce mold growth and push you into the fail criteria under DA07. There, you can see 3 boards there that are inducing a higher risk of mold growth because they're very high vapor resistance. So we're talking about OSB4, which is a high vapor resistance OSB, and high vapor resistance plywood that starts to create problems even with an intelligent air barrier on the inside of the structure. So do not use high resistance sheathing boards is the message there. If we go to Sydney, similar outcome, and the same message: do not use high resistance sheathing boards because you still run the risk, even with an intelligent air barrier, of trapping humidity behind that exterior rigid WRB system. So in the cooler regions or in the mixed climate regions of Australia, you're probably far better off using an intelligent air barrier on the inside of the structure in combination with rigid weather resistant barrier systems on the outside of the structure. And this is how we develop healthy, durable and energy efficient systems. So for more information, please contact us, ProClimate in New Zealand or Australia. Just give us a call or email us. Thank you very much.